Okay, let's revisit what we know and put the totality of our understanding on the board in one shot. What mechanisms do we know? Okay. In an elimination, what's my reactant? So I'm going to have two reactants. One is the carbon chain that I am physically altering, and we'll have that be reactant 1. And then reactant 2 will be the agent of cause that is causing my carbon chain to become the new thing. In an elimination, what's my carbon containing reactant? I know it's been 2 weeks and we barely found our way back to campus and knew which room we were supposed to be in and all of that important stuff, but come on. What would be a viable reactant for an elimination reaction? There you go. Why did you pick haloalkanes? Because it has a leaving group. In an elimination, you have to have the leaving group leave. Okay. What is it that's going to make my leaving group leave? And what is the product of an elimination? I've taken a haloalkane and some base, and I'm going to do this elimination reaction. What is my product?
Alkene.
Alkene. All right. What is the second product? Furrowed brow. What on earth is he talking about? Second product. That's the thing that makes you go from being a 9-point correct answer on the test to being a 10-point correct answer on the test. It is the mass balance. It is what happened to your base. Plus, where did your leaving group go? What conditions might we put into place above or below? Usually write reagents above the arrow and then conditions below the arrow. What conditions would we write below the arrow to make this reaction more likely? Heat. Okay. So, write a haloalkane here. Write a base there. Move the arrow from the base to somewhere in that haloalkane. Make that haloalkane give up its leaving group. Write me the appropriate alkene and balance it. Go. First one to finish, stand on the desk. And raise the completed mechanism in the air. We should have door prizes. Now, while writing your mechanism, you may have got to the point where you go, ah, I remember or half remember that this mechanism has two flavors. I didn't specify anything. I just said, you do it. Who has one? What was the name of your haloalkane, Miranda? Okay. First question, why'd you make it so big? No, 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 no. All right. Yeah. So, 2-chloropentane. Okay. Oh, wrong place. Chloropentane. Which base did you use?
I don't know if I used the right one, but I just picked an AOH.
Fabulous base. Now, we've not been balancing stuff because we don't need to. Because it's organic chemistry, we don't balance it. But when it says water plus salt over here, it sounds a bit, first of all, that sounds a bit like a neutralization reaction, because there is an acid in this solution and there is a base. It's going to be the salt. So I've got some sodium plus and some hydroxide. All right. There's going to be at least one arrow in this mechanism. Where does the first arrow start from?
The area of high electron density.
The arrows come from the place on the page where the electron density is the highest. Where's that?
OH.
So that's where my arrow is going to come from. Where does it go to?
You just smell like
The who?
medicinal hydrogen, that's it.
This is an elimination. So it's going to make me an alkene. So what I'm doing is I'm removing HCl. This is a dehydrohalogenation. I have 3 hydrogens that are one group away from my leaving group. Or these 2 hydrogens that are also one position away from my leaving group. We had said that this is a base. We had not used the word nucleophile. What's the difference between a base and a nucleophile? People in the back, what's the difference between a base and a nucleophile? Bases grab hydrogens, nucleophiles grab carbons. This is a base. Which hydrogen does it take? We call them 1, 2, 3, 4, 5. Yes is not a correct answer.
4 or 5.
4.
4 and 5 are equivalent to each other, but I'm not going to take 5. Why not? I'll show you why not. Because if I take 5, now am I taking this as an H atom?
H plus.
No, I'm taking it as H plus, because H plus and OH minus cancel each other out and make H2O. So I'm taking this as H plus, which means it's going to leave its electrons behind. It's going to make the double bond right there. Oh, I just went over another atom. My arrow had to go over another bond. That's why I'm not going to take number 5. Nothing wrong with taking number 5, but it's not as clear to the reader. As if you take number 4, taking that H as H plus, just the proton, no electrons. Okay, these 2 electrons can now go between those 2 carbons, and I just made a double bond. But that carbon already has 4 bonds. And I just made a new bond to it. So something has to go. And it's this. Now, why did I take either hydrogen number 4 or hydrogen number 5 and not hydrogens 1, 2, or 3? There's more of those. There are more hydrogens here. Why did I not go where they were plentiful?
Sips.
Because of Zaitse's rule, and Zaitse's rule in a sentence says, in an elimination, give me that phrase, the clause at the beginning that says this is the type of reaction that Zaitse's rule is in operation for. In an elimination, the most substituted alkene is the most stable product. Probably made more often. So if I'd have taken a hydrogen from carbon number 1, I would have made a terminal alkene, and terminal alkenes are not as good as internal alkenes. So make the most substituted alkene. Okay, that gives me my alkene. That OH minus picked up an H plus, made H2O, and then here's the salt. This Na plus that we never really wrote down, it's not part of the mechanism, it's a spectator ion. It's just carrying the hydroxide, just carrying the base. This is performed in a protic solvent. That sodium chloride might, well, will not be intact. Will still be dissociated and ionized and floating around. If you do this in something where the ionic salt is insoluble, then it will sink to the bottom of the flask as a precipitate. Okay, what is it that's described on the page right now? What have we just done?
And E2.
That's an E2. How do I know it's an E2?
You have a strong base.
Okay. It does have a strong base, but I can do E1s with strong bases as well. Because for an E1, the base doesn't matter. So an E1 will work with anything. How do I recognize that this is an E2?
It's unique. It's inserted.
This is an E2 because that and this and that all happens in one step. Okay. That's an E2. Here's my task for you right now. I want this alkene, there it is, it's the same as that alkene. I want you to make it again, but I want you to choose a different set of reactants so that you can demonstrate the E1. Think, go, do. E1. What's the big difference between an E1 and an E2?
The leaving group leaves first.
Leaving group leaves first, and that gives me something that is not in carbocation. So, give me a situation where you have a reactant. Leaving group leaves behind a viable carbocation. And then instead of losing the H and the leaving group in one go, you lose the leaving group, and then you lose the vicinal H, but you still make the same product. Everything else can be different. Delaney, what was your reactant? But you did so much writing.
I was making my chart.
Okay.
Sorry, I don't know.
Okay. It looked like you were writing and you put your pen down like, oh, yeah, I got this. Anybody prepared to propose a new reactant?
2-bromopentane.
2-bromopentane would also work. Did anybody do anything other than 2-bromopentane? Okay, we'll just do it after. All right. In an E1, I also have curved arrows. Where does the first curved arrow go?
The bond between the bromine and the carbon. Or the carbon, yeah, carbon.
Going to allow the leaving group to leave, I want to say of its own free will, but that's not completely true. What is promoting the leaving group from leaving?
Electronegativity.
Who?
The solution needs their own.
Good old-fashioned general chemistry solvation. I'm going to have a neutral molecule turn into two charged ions. I'm going to have charged ions in solution. Then I better have set up the situation to promote that. I'm going to need a protic solvent. Examples of protic solvents are, this is where you talk.
Alcohol? Or
Yeah,
alcohols?
alcohols will do. Alcohols are protic.
Acetone?
Acetone is polar, but it's aprotic. How do we spot the difference between protic and aprotic? What is the thing to look for?
Hydrogen bonds.
The hydrogen being directly attached to the electronegative atom. So anything with an OH, anything with an NH, although NH bonds stick. And unless you're working in liquid ammonia, which is a good solvent, but it has to be cooled to negative 40. And anything, all the other regular amines, they're going to smell. They're going to stink up the joint. Alcohol water. I'm going to promote that solvation right there. Okay. That solvation is solvolysis is slow. Okay. I'm going to need a base. What base should I use? Doesn't matter. Use anything at all. Absolutely anything. Your reactant is already in alcohol or water. So the presence of an external base might not even be necessary. Maybe not. But if you were to use hydroxide, that would be fine. It would just do exactly the same thing that you did before. Heat always favors the elimination. And again, we would make H2O and we would make sodium bromide. Okay. Okay, that's fine. I've introduced the mix now. This first one had this arrow, and that arrow means these reactants have turned into those products. And I can be relatively certain that has happened because this has a negative charge, and that negative charge is on something from the right-hand side of the periodic table, but not a chlorine or a bromine. So something, not the extreme right-hand side. So that's a good base, which means whatever bond it just made, that bond is probably going to stick. And so this will turn into that. This first step has no driving force. That bromide can leave. But there's a negative and a positive here. Why can't I just have that reattach? Backwards and forwards and backwards and forwards and backwards and forwards. Okay. So some reactions will have, and once this thing shows up, yeah, now you've made the alkene. But some reactions don't have a driving force when the reaction doesn't have a strong base or strong nucleophile. On this side, maybe you have to use these arrows. Okay. So you can keep what you've got, but for the sake of space on the board, I'm going to erase it all again and tell you to do that problem again. Only don't use a halo alkane. Give me a 5-carbon molecule to start with that is not a haloalkane. And what I'm specifically looking for is, I don't want that arrow. I want this arrow. Now the thing, it's in the arsenal of all those reactions that we did in Organic 1. It's in there somewhere. That reaction is a dehydrohalogenation because you lost an H from one carbon and you lost the leaving group, the Cl, from one position away from it. Other than a dehydrohalogenation, what other kind of elimination did we learn about?
Analysis.
Instead of removing an H and a Cl, go ahead and remove an H and an OH, which makes this reactant be an alcohol. See that leaving group? That leaving group left became chloride. Chloride is a weak base. And weak bases are good leaving groups. Compare and contrast chloride, my leaving group in the top example, to hydroxide. That's my that's my leaving group in the bottom one. This is a strong base, so it's not coming off. Bases make bonds. If that's a strong base, then it is not a leaving group. So why have I told you that dehydrations are possible? Because we did them. The secret to oxygen chemistry was what? Protonate the oxygen. What arrow, so the curved arrow shows the motion of 2 electrons. H plus, that's my area of low electron density, that's an acid. And a lone pair of electrons, that's a base. Base sees the acid, base reaches out with the curved arrow and grabs the acid. That does not warrant this type of arrow. OH minus to H plus gives me that arrow. But whatever I've got going on here to that H plus does not. That's a strong base. This is a weak base. This has a strong driving force which pushes the reaction forward. This one is a weak base. It's bases that make bonds. Therefore, we're not pushing this reaction forward. I don't get the right to use that arrow. I have to use this one. I have a protonated alcohol. What should I be noticing and recognizing now?
Has too many bonds.
Yep. And a charge. Which means that that oxygen is now the leaving group. Let's have it leave. If I want to have this be a leaving group, and it's an E1, remember it's an E1, I'm going to leave behind a carbocation. Where does my arrow start?
The electrons, yeah, the electrons between that oxygen and carbon.
I'm putting a lone pair of electrons back on that oxygen. I'm taking this bonding pair of electrons between the oxygen and the carbon and turning it into a non-bonding pair. Again, there's no powerful base pushing that forward. This gets to be in equilibrium. Does my carbocation and there's the water that I just lost. All right, now the base can come into the picture at this point. Still doing an elimination, which means I'm either taking one of those three or one of those two. And Zaitsev says, don't you dare take those. Take this one. I still need a base. What's my base?
Sodium hydroxide.
All right. If I add sodium hydroxide
Oh.
into this reaction scheme, what happens?
Make alcohol.
You kill the acid that's floating around that just protonated the alcohol so that I had a leaving group. Now I don't have a leaving group. So that is not the correct answer. A base would eliminate the possibility of me having a leaving group. What is the base? It's right there. So a pair of electrons on the alcohol, on the water. Or on another molecule of alcohol. That's the most basic thing in solution. This reaction is in acid, therefore there will be no named base. There is no hydroxide or methoxide or anything else that you've come to know as a good powerful base. The strongest base is now a lone pair of electrons. And there you go. We just jumped from there to here. And we made our side product, protonated water. And that's it, right? trick here. What am I thinking? These are all in acid. If you put your reaction in acid, first step, this reaction goes in acid, then you may only have positive charges in your mechanism. If at any point you start off a mechanism in acid, and then, oh, Mr. Hydroxide appears in step 3, you're going to have to rethink that. Because Mr. Hydroxide is going to just stamp the acids to death. And without the acid, the alcohol doesn't get protonated, and therefore the leaving group doesn't leave. So base would not help this reaction, it would actually hinder it. So in acid, you only get positive charges, and because you're performing this in acid, there is no strong base, and it's the base that is the driving force for all of these reactions. Therefore, you cannot use the regular arrow. All of your reaction steps will be equilibrium. Okay? How many mechanisms are we going to have on our page? We've done 1. What's left? What type of substitutions? Nucleophilic substitutions. And then what else? What type of additions? Electrophilic additions. So I've got 2 other mechanisms that are going to go on this page. As a reminder, here's some homework. It may actually be a repeat. I may have given you Organic 1 students from the fall this to do already. I'm not sure. Friday. Friday. Huh? Right now the syllabus says 10 o'clock. That seems to be working for me. Although my afternoons are now freer than they used to be. So I'll let you know if I'm going to change the office hours. I would say don't show up for lab at 8 a.m. I would say don't. I'm going to see if I can put